Have you ever wondered how a group of diverse opinions often leads to a much better decision than any single expert could make alone? In machine learning, we see a similar powerful principle at work, especially when tackling complex prediction tasks. The core steps of the bagging ensemble, which stands for bootstrap aggregating, involve creating multiple versions of a model from different subsets of the original data, and then combining their predictions. Specifically, the process begins with resampling the training data using bootstrapping, training a base learner on each resampled dataset, and finally, aggregating the predictions from all these individual models to form a final, robust output. This approach is highly effective because it directly addresses the problem of high variance in machine learning models, especially with complex ones like decision trees. By generating numerous diverse training sets through random sampling with replacement, bagging ensures that each base model sees a slightly different perspective of the data. When these individual, often unstable, models are then averaged or voted upon, their errors tend to cancel each other out, leading to a much more stable and accurate overall prediction. To implement this, you would first perform bootstrap sampling on your original training dataset, creating many new datasets of the same size. For each of these bootstrapped samples, you train a distinct base model independently. Crucially, these base models are typically of the same type, such as decision trees, but they learn from different data subsets. Once all models are trained, if you are predicting a continuous value, you average their outputs, or for classification, you take a majority vote to determine the final prediction. An interesting aspect of bagging is its inherent ability to provide an out-of-bag error estimate without needing a separate validation set. Since each base model is trained on only about 2/3 of the original data, the remaining 1/3, known as the out-of-bag samples, can be used to evaluate that specific model. This internal cross-validation helps estimate the generalization error of the ensemble. Furthermore, bagging is often paired with weak learners, like unpruned decision trees, as it excels at reducing variance without significantly increasing bias. Ultimately, by strategically using random data sampling and combining multiple individual models, bagging provides a robust and powerful method for improving predictive accuracy and reducing overfitting. It allows us to leverage the collective intelligence of many models, ensuring a more reliable and stable performance on unseen data, which is essential for real-world applications.